Okay, so let's talk about section 4.1, the transformations of graphs and symmetry. As we take a look at this, you're definitely going to want to kind of look at the equations, and we're going to determine whether or not those graphs of the functions that we're looking at have been shifted, whether it's vertically, horizontally, stretched, or compressed, or even reflected. And then while we're also looking at those graphs, we are going to look at whether or not they're symmetric about maybe the y-axis, the x-axis, or the origin, which leads into determining if the functions are even odd or neither. Okay, so you might want to go ahead and pull your graphing calculator out. So if you've got a graphing calculator, it's definitely going to help you out here. So let's start with graphing two functions. Let's graph f of x equals x squared, and we're going to graph g of x, which is going to be x squared plus 2. Okay, now we want to graph them on the same axis. So since we're graphing these, go ahead and put this one in y1 and this one in y2. Okay, so we're going to graph them. And again, for those of y'all that have a TI-83 or a black and white style screen, be really aware of which one you put in y1 and which one you put in y2. And the reason why I say be aware of that is because whichever one is put in y1, that's the one it's going to graph first. So as you watch it, it will actually graph the first one, and then it'll take a second and graph the second one. And you really kind of want to pay attention to that. For those that have color screens, it's going to be a little bit easier because you're going to be able to see the visual change in the color. So take a peek at that and make sure that you kind of see that difference. So I went ahead and graphed them for you. And so the blue one, that is going to be my beautiful f of x. And the red one there is going to be my g of x. Okay, so if you were to watch it graph, you're going to see the blue one graph first, and then you're going to see that red one graph second. So by looking at this graph, one of the things I begin to notice is that I'm noticing that we've got this, okay, it's graphed, but it's a parabola shape. And we talked all about parabolas previously before, so parabolas are a great one to look at. But what I notice here is the vertex. And the vertex from here to the first one versus the second one, so the blue versus the red, the vertex looks like it's just been basically shifted. And it looks like it's been shifted up. Okay, now how many units has it been shifted up? Well, 0, 0 is that beautiful vertex on the f function. And as I look onto the g function, it looks like it's been basically x equals 0, y is 2. So it's been shifted up 2 positions, which again, we can see it reflected over in the table as well. But as I kind of look at it visually, I can very well see that it's been shifted up 2 units there. Okay, notice the difference between how we wrote the equation. So on this one here, it's just f of x equals x squared. And this one says g of x equals x squared plus 2. So really, this is the only thing different between these two. And I notice that it's been moved up 2, and there's a beautiful plus 2 that kind of makes that different. So let's try this again, but this time let's put in x squared into our y1. And in y2, we're going to do our g function, which is x squared minus 2. Okay, and let's graph them at the same time. So again, my blue one there is going to be that nice, lovely f function, and then the red one there is going to be the g function. Okay, now again, as I take a look at this on my going from my f to my g function, how are they related? It kind of looks like if you took that f function, it looks like it's been kind of shifted down. And again, I'm looking at that point 0, 0. 0, 0 is a great point to look at on the original graph. So that f function that we graphed first versus where is it in that second function, which is the g function, that y sub 2. And I'm noticing it looks like it's been moved down. Now, what's the biggest difference between these two graphs when you write the equations out? Well, it looks like the only main difference is the minus 2. But I also see visually that it looks like it's been shifted down 2 units. So a minus 2 going down 2 units there. And that's actually what I kind of want to pay attention to. So this is actually a sign of a vertical shift on a graph. So if you have some number, we'll call it k here, and you know that you have basically a graph, and then you took that graph and you kind of shifted it, okay? If I basically take the base function of the graph and I shift it kind of plus k, we can say that basically we have shifted the graph up or down by saying plus k or minus k. Okay, now f of x here I'm referring to as basically what we call a base type function. So you'll notice that when we started off, I said, well, f of x equals x squared. And then on my first example there, I gave us g of x was x squared plus 2. And notice the big difference between this one and this one is that plus 2. And we saw that the graph kind of looked like it went up 2 units. And then when I tried it again, graphing f of x equals x squared first. And then the second time when I graphed it, we said x squared minus 2. And on this one here, again, the only difference between x squared and my g function is x squared minus 2. That minus 2 is the only thing different. And we saw that this graph kind of went down 2. Okay, and that's actually what we're looking at here. Now, when we refer to this f of x here, sometimes we give it a name. And so when we talk about f of x, sometimes we call this our base function. Okay, or sometimes we might call it what we call a parent function. Okay, so either or, they're kind of the same thing. Either one of those names will work there. And what I mean by base function is what is that basic shape of the graph? Okay, so we're going to continue on with the x squared, our quadratic, and that's going to really kind of help me visually see the rest of these graphs. So let's graph the function. Again, our base function, our parent function. So here's my base. We're going to start with this x squared. But this time, my g function is going to be the parentheses of x plus 2. And outside that parentheses, on the parentheses itself, is going to be the power of 2. Okay. And let's see what type of relationship we notice between these two graphs. Okay. So as I graph those two graphs, again, that f function is going to be the blue, and that g function is going to be the red there. What I begin to notice as I look at this graph, again, I'm kind of paying close attention to that vertex because that vertex actually tells me an awful lot about this graph. Is I notice that it looks like it's been kind of moved over left 2. And that's basically what it has. The graph has actually been shifted left 2 units. Okay, well, what if I change that from a plus 2 to a minus 2? Okay, again, keeping that same parent function, x squared, but the only difference is I'm changing it from a plus to a minus. So again, as I take a beautiful peek at those graphs there, again, the blue is still going to stay the f, and the red is going to stay the g there. And I notice, again, really paying very close attention to that vertex. So the vertex on the f function and where the vertex is on the g function, I'm noticing it looks like it's been shifted 2 units, but this time it's been shifted to the right. Okay. Now, what was the main difference between my base function and its equation and the shifted function's equation? Well, really, it's just this minus number here. So when I said minus 2, we see that the graph actually moved to the right. And when I said plus 2, it actually moved to the left. And that's actually what we really kind of want to notice there. This is what we lead into what we call a horizontal shift. So horizontal shift is basically when we talk about moving, in our case here, left or right movement. And when we talked about vertical, vertical meant up or down. So left or right for horizontal. And the big difference here is that we're going to take our base or our parent function there, and everywhere we see x, we're replacing it with x plus or minus a number. So let's take an idea of this. So let's take our base function there, and let's just call it f of x equals, let's go with our x squared. We'll keep it with x squared because that's kind of our nice idea there. And in our case there, let's say our g function, in our case here, is now going to be x plus 3. Now, in my sense here, now normally when I see the word plus 3, I would say up or down. However, notice where it is. And that's the part that really you kind of want to pay attention to. Notice that it looks like it's kind of trapped inside a set of grouping symbols. Okay, so it's kind of where I would have plugged in for exactly what the variable would have been. It's been kind of plugged inside of where that was. So I notice that it's +3 inside here. So that +3 inside automatically tells me that it's going to be 3 units. Okay, so that's where I'm getting the 3 from. So 3 units, but the plus sign is actually telling me that I'm going to move left. So 3 units left. Now, if I were to take that same function, but this time maybe change it to say an x minus 4 quantity squared. Okay, again, kind of really noticing that we've got a set of grouping symbols here. And again, that's kind of what I'm really paying attention to. And it's that grouping symbol is kind of replacing where I would normally have just a plain old Jane X there. But what I do notice is I notice that I have this kind of -4, which is a little bit different. So last time I had a +3, this time I have a -4. Now with that -4 that I see there, I kind of want to see that and go, okay, well, that's going to be 4 units. Okay, so I'm just going to take that number, whatever that number is, that's kind of that number, the unit number. But the minus sign is telling me that I'm actually moving to the right. So let's try this with a couple of other ones. And let's look at some of the other possible transformations that can happen to a graph. So let's graph the function f of x equals x squared. And my g function is going to be that parentheses x plus 2 quantity squared plus 1. And again, we're going to graph them on the exact same axis so we can see the big difference between the two. So as I graph the first one, again, we're going to start with that kind of base parent function, okay? And that's what we kind of want to plug in y1. And in y2, I'm going to do my kind of transformed function, okay? Now you can do this visually, or you can even do this by looking at the actual equation. And notice in the equation, the big difference between my parent function and the function that I have for that g of x, or that y2 that I'm going to plug in, is that there's a +2 and a +1. What does that +2 and that +1 actually mean? Now, what I suggest doing is kind of look at where they are located. So notice that +2 looks like it's inside some grouping symbol, and that +1 is outside the grouping symbols, okay? Anything that is outside the grouping symbol is going to be some type of vertical movement. Okay, and anything inside the grouping symbol is going to be a horizontal movement. So outside is vertical, inside is horizontal. So +1 on the outside is a vertical movement. Now, how does this graph from the blue? Again, the blue is the first one. That's that y equals x squared, or f of x equals x squared. That's the blue. And the red one is my g function there. And how do I see how's it moved vertically? It's been looking, again, kind of pay attention to that vertex there. It's really helpful there. It looks like that vertex has been moved up. Now, how many units has it moved up? It's only moved 1 unit up. Now, that +2, again, that's inside. So that would be a left or right horizontal style movement. So if I, again, take that vertex, it's already been moved up, but now it looks like it's been moved left or right. Well, in our case here, it looks like the graph moved left. And again, that +2 on the inside tells me that the graph has shifted left 2 units. Okay, well, let's compare the following graph. So let's look at y equals k times x squared, and let's actually graph it with the 3 different k values. Let's put in k equals 1, 3, and 1/3. Okay, so we'll start with our first one. When I plug in k equals 1, that's going to be y equals x squared. And then when I plug in k equals 3, that's going to give me 3 times x squared. And then when I plug in 1/3, it's going to give me 1/3 x squared. Okay. Now, previously, we've looked at this kind of y equals x squared. And I keep saying that that's my base or my parent function. Okay. So this is kind of the one that we're going to look at and compare how does it change to the other two. So again, y equals x squared is just a very basic quadratic equation, which means it's going to be a parabola style. And again, that vertex there is 0, 0. Okay. I also want to kind of notice that in this one here, it looks like I've got a point here at 1, 1 and -1, 1. Okay. And then I can see there at when x is 2, my y value is 4, and when my x is -2, my y value is 4. So those are some key points to kind of pay a little attention to. And we can kind of see what happens to it. So I'm paying attention to like these points right here. And again, why are these the points I'm paying super close attention to? Well, these are the points that we can see the most. One, they land on kind of grid lines, but this will kind of allow me to look at other graphs and go, okay, what exactly happened to those points? So let's look at y equals 3x squared. Now, if you take a look at this one here, again, what I want you to notice is where did I put that 3? I put that 3 outside kind of the base shape of the graph. There's no grouping symbol, so we always say that's outside. It's not inside any group, okay? And anything that's outside is always a vertical style movement. Now, in our case here, it looks like I've actually taken that graph and I've kind of stretched it, because notice what happens at -1 and 1. So at -1, my graph now has a y value of 3, and +1 also has a y value 3. Now 0, 0 stays where it is. So I literally have kind of pinned down that vertex, but it looks like I've taken that graph and kind of stretched it up. Now, if you look at x equals 2, notice that it's so far up here, it's like I can't actually see it anymore. So it looks like we've actually taken that and pulled it. Now, if I were to take this in and plug in x equals 2 here, 2 squared is 4, and 4 times 3, which would give me 12. So this point is way up here at 12 for the y value. And this point here is way up here, again, still at that y equals 12. Okay, so these points are still there. It just looks like they've been kind of stretched out a little bit. Okay, so let's look at and change that k value to 1/3. What happens to that graph then? Well, the graph, again, still has those key points that I'm kind of looking at. So I'm still looking at 0, 0 there, but notice at -1, it's kind of here. Now, it doesn't actually land on a perfect grid line. So let's take a look at that number, x equals, say, 2. So at x equals 2, I'm kind of here. Again, I'm not landing on any perfect grid line, which is a little unique there. But what I kind of want to notice is where did it go from? So here I went from like x equals 4, sorry, y equals 4. So when x equals -2 or +2, my y value is 4, right? But notice on this case here, at x equals 2 and -2, my y value is smaller than even 2. It's kind of like in between 1 and 2. Okay. And when I look at -1 and +1, again, it's even smaller than 1. It's in between 0 and 1 on those y values. Now, how exactly is it changed? Well, it looks like I've basically taken the graph and kind of vertically compressed it. Again, that 0.00 is still exactly where it is. It looks like I've just kind of taken that graph and like smashed it down. So I kind of smashed it this way and this way. So it's what we call a vertical compression. Now, our vertical compression is by a factor of 1/3. Okay, meaning that basically I compressed it down to where it was a little bit smaller by basically all the y values changed by 3. So if you actually think about that, and that's kind of where you want to look here. Here was the y value on the original graph was 4. 4 divided by 3 is 1 and 1/3. So that's kind of where that went. And again, here my y value was 1. And again, 1 divided by 3 is 1/3. Notice again that y value looks like it's about 1/3 there. So we can kind of see that these have been vertically compressed. And that's actually one of our other types of transformations we do, stretching and compressing. Now, I know the word compress probably sounds a little strange there. So let me write it slightly differently. Instead of thinking compress, think about shrinking it. Okay. So when I think about that word there, we're basically vertically stretching or compressing it. Now we like to use the word compress because that sounds a little bit better. And that's really what we're doing, is we're kind of compressing the graph. But basically you're kind of just shrinking it down a little bit, and that's literally what you're doing. Most people use the word shrinking, but the actual terminology is compressing. Now, how I'm going to know whether it's a vertical is basically look for a number on the outside of that parent function, that base shape of the graph. And it's always going to be, if it's something bigger than 1, it will be a stretch. If it's anything between 0 and 1, it's going to be a compress or a shrink there. Now you'll notice I said that that was a positive number there. I didn't actually talk about negatives because that's actually something different. So if it was negative, the negative actually deals with what we call a reflection, and it's reflecting. If that negative is on the outside, we reflect on the x-axis, and if that negative is on the inside, we actually reflect on the y-axis. Now, again, I know this sounds like really kind of just a little weird there, but let me explain, and it might help a little bit if you think of it in terms of this. So I'm going to kind of draw 2 grid lines. Again, I'm not drawing perfectly, so we just need to get the basic idea here. So if I were to take a graph, okay, and we'll say, let's look at x cubed. So here is y equals x cubed, okay? And I'm going to draw both of those that way there, okay? So we're going to use f of x equals x cubed. So there's my basic x cubed graph, okay? So one of the things that when we look at that, we can look at it 2 different ways. So if I were to take it and actually take that function, and we're going to change it just slightly, and I'm going to put a negative in front of that x cubed. Okay. When I plug a negative in front of it, that negative is on the outside of the shape. There's no grouping symbols or anything there. And what that actually does is it actually takes that graph and basically takes it and flips it across the x-axis. So this part of the graph now goes down here. And then this part of the graph here goes up here. So the graph ends up looking like this. Okay. And we can kind of take that and really kind of take a look at it. And we're like, okay, I can see that a little bit better now. Okay. Let's try this again, but let me change it up a little bit. I know I said I wanted to use x to the 3rd, but that's a really good one there. Let's look at, how about, let's look at the square root. Okay, so on this one here, I'm going to use f of x being that square root of x. That's a really good one here. Okay, so on this one here, I was just using x cubed, and this one here, I'm going to use the square root of x. So that way we have a little bit better of a visual on it. Okay, now again, you can put these in your graphing calculator. I'm just drawing them by hand because it's a little bit easier to maybe visually see it by hand when I draw this. So if I were to take that graph, and instead of saying the square root of x, I say the square root of negative x. So I put a negative underneath there. What that's going to do is that negative, notice that negative is inside a set of grouping symbols. Now, my grouping symbol does happen to be a square root symbol, but that's perfectly fine. What that's going to do is that's going to basically take my graph, okay, so the base function that I have of the graph here, and it's going to reflect it across the y-axis there. So the graph is actually going to look like this. So it looks like it's been mirror imaged across the y-axis. Whereas if the negative is on the outside, it's a kind of vertical flipping upside down. Whereas if it is inside the grouping symbol, it's a horizontal flipping, meaning just kind of a left and right flip. Okay, and that's actually kind of what you want to pay attention to. Are we inside or are we outside? If we're inside, we are doing everything horizontally, and if we're outside, we're doing everything vertically. So let's take a peek at this lovely thing. Let's first start by determining our parent function, and then we're going to describe the transformations on it. Okay, so to start us off there, the first thing I say is I need you to figure out what the base or the parent function is. Now, the best way I can actually help you here is take away anything that's being added, subtracted, multiplied, or divided. So just kind of cover it all up. So if you'll notice, I kind of covered up my negative number, my 3, my -5, and that +4. I just kind of covered them all up there. Leave exponents alone. That's the only thing that you're allowed to keep that as a number, okay? Don't cover up any symbols. Don't relocate X. X stays where it is, okay? So just kind of cover up anything that is there and that is being added, subtracted, multiplied, or divided, okay? Added, subtracted, multiplied, or divided. If you cover those all up, you're left with this kind of X to the third power. This is what we call our base function. Okay, so my parent or my base function in our case here is y equals x to the third. And again, you kind of want to draw that in your y equals so you can kind of get an idea. And the first point that I'm really going to pay super close attention to on this is going to be 0, 0. Again, that's kind of a great point to watch. You can also watch a couple other points like you can do 1, 1. Or even -1, -1. That's also a good one to look at. Now, you'll notice I covered everything up. So we want to actually describe what each one of those transformations are. So we're going to start with the innermost grouping symbol first. Okay, so inside the set of parentheses, there was a -5. So what I want to do is I actually want to plug this in the calculator. And in that calculator, I only want to graph this part of it. Okay. So let us pull up our calculator, okay? And in our calculator, let's take a peek at what that does. Okay, so I've gone into y equals on my calculator. And again, remember when I said figure out what that parent function is? Go ahead and put that first. Now, in the y sub 2, now I've got the entire function put in right now. But what I want you to do is I want you to go back in there and kind of delete anything out that was not inside the grouping symbols. We only want to look at one little part of it at a time. Okay, so we just want to look at this one part. If you'll take each one of those numbers part by part, you can actually visually see the transformations happening. So if I were to hit graph right now, again, there's that parent function. And then notice that -5 inside the parentheses. Again, the -5 was inside the parentheses. What looks like it happened to the graph? Well, because it's inside the set of parentheses, it's a inside movement. All inside movements are horizontal. And in our case here, because it is a +5 or a -5, again, that is a left or right movement. The plus or minus of a number inside the grouping symbols is always a left or right movement. Now, in our case here, it was a -5, which means we are moving to the right. And again, I can kind of count that out. 1, 2, 3, 4, 5 units. And again, that's kind of why I was paying attention to that 0.00. I can see that that 0.00 has basically moved to basically be x equals 5, but my y value is still 0. And again, it looks like the whole graph has just moved over. Everything else just kind of looks like it shifted over 5 units to the right. Okay, so basically that -5 inside the set of parentheses there basically just means that I've shifted it to the right 5 units. Now, let's ignore the -5 and take the next number. And again, we're kind of starting with the inside and then working our way out. So the next thing outside the set of parentheses is the 3. Now, again, you'll notice I covered up the negative sign because they're technically something different. When we talk about multiplication of a number, we always talk about that multiplication of the positive version of the number. The negative meant something different. So again, I can take that graph and put it in there and just put the 3 in front. And again, kind of ignore that -5. And take a second and think about what happened to the graph itself. Now, I'll give you a bit of a hint. Notice that 3 is outside of the parentheses or grouping symbols. So that right there tells me that it is a vertical. Okay, anything inside is horizontal. Okay, anything that is outside is always going to be vertical. Now, in our case here, it's vertical, but it's multiplying. So vertical is going to be a stretch or a compress when you multiply by a number outside the parentheses. So it's a vertical, stretch, or compress. Now, if it's outside, it's going to be exactly what you think the number represents. If you're inside, remember, it's kind of opposite of what you wanted it to be. So when I see the word, when I see the number -5, I really want to say left, but because I'm inside, I have to go backwards and say right. Whereas if I'm outside the set of parentheses, when I see multiply by 3, I'm actually going to think that I'm going to stretch by 3. Okay. Now, let's deal with that negative. Again, and I am on the outside there, so it's going to be a vertical. Again, I'm multiplying, so that is going to be a reflection. So it's a vertical reflection. And if you have to think about that, a vertical reflection, vertical is that kind of Y value that we're looking at. So it means that we're either moving the graph up or down, or we're vertically reflecting, which would basically be the same thing as a reflection on the x-axis, because that's what we flip over vertically there. Now, the last thing that I look at is going to be that +4. Again, it's on the outside, so I'm going to say the word vertical straight away. But anytime that I add or subtract, that is a movement of like up or down. Okay, so it's a vertical up or down. Now, again, if it's outside, it's exactly what you think it is. So +4 makes me think I'm going to move up 4 units. Okay, so we've got all of that transformations there. So we've shifted right 5, we've stretched by a factor of 3, we're a reflection on the x-axis, and we moved our graph up 4 units. And again, I can kind of graph all of them at the same time now, and I can see that happening. Now, it was a little hard to see when I graphed all of them at once. So if I did each one individually, it really allowed me to see the individual, what each number represented. Okay, and so there's 4 different transformations on this graph itself. Okay, so there was a couple other ones there, so I do want to talk about them as well. So we kind of talked about that moving the graph up or down. We talked about moving the graph left or right. We talked about its reflection, whether it's on the x-axis or the y-axis. We talked about a vertical stretch or shrink. There is such a thing as a horizontal stretch or shrink, and the horizontal stretch or shrink is going to be, again, anything inside the parentheses is horizontal. So if I'm multiplying inside the grouping symbols, it is a horizontal stretch or shrink. Now, again, everything is backwards from what we think. So if I'm multiplying by a 3 inside the grouping symbols, that's actually going to be a compression. And if I am multiplying by, say, like a 1/2, I am going to be stretching horizontally. Okay. So it's again, everything is backwards when you're inside. So I know when you multiply by 1/2, you think you're getting smaller, but it's not actually getting smaller. It's actually getting larger because it's inside, we're backwards. Okay. So let's actually try to create the equation. So I've already given you what the base function is. Let's actually create the equation by, I've told you what the actual shifting has happened, like what type of shifts we've done on the function. So what would the new equation look like? So I'm going to give you, our parent function is going to be y = x², and I want to shift it down 1 unit and left 4 units. Okay. Down means it's vertical, right? And left means it's a horizontal movement. So again, vertical should be inside, horizontally should be, vertical means it should be outside, and horizontally means I'm inside. Okay, vertical, outside, horizontal, inside. So inside, when I say inside, I mean inside a set of grouping symbols. Now, there's no grouping symbols automatically put here. So what we do is we take our base function and we actually plug a set of parentheses in for it. So I'm going to put some parentheses and then my power of 2. And then inside those parentheses, I'm going to put my left 4. So again, +4. And then outside the set of parentheses is going to be my vertical movement. And again, I'm just going to put that as a -1. Now we can graph this to actually verify our results that it actually moved left 4 and down 1. Let's try this again. So let me give you a function, f of x is equal to the square root of x, and we're going to compress it vertically. Again, keywords there. So we're going to compress vertically. By a factor of 3, we're going to reflect on the x-axis and we are going to shift right 2 units, okay? And then we are going to go down 3 units. Okay, so what exactly will that new graph look like? So let's just start with our base idea there. So we've got that kind of y equals that square root of x. And again, this part here will be my inside area, and anything outside, and I can put it in front or back here, this is kind of my outside area. Now remember, outside, this is going to be anything that is vertical. So any type of vertical movement is outside, and inside is going to be anything that is horizontal. Okay. Now, compress vertically, so that means I got to go outside there. Reflect across the x-axis. Now, again, I forget which one it is. So let's just draw our grid lines there. Here is my x and here's my y. So I'm reflecting across the x-axis. So that looks like I'm vertically reflecting. So that should go on the outside. And I'm going to shift right 2 units. So right 2 units would be kind of to this direction here. And again, as I shift to the right, that is a horizontal movement. So that's going to go inside. And then when I shift down, again, down, that's a vertical movement. So that should be on the outside there. Okay, so let's put that all into play. Okay, now when I start taking a peek at all of this here, when we do our compressing, now I said the word compress, which means I'm making it smaller. Now, even though I said compress by a factor of 3, I'm actually compressing by basically changing everything by a multiplication of 1/3. So it's like you're dividing everything by 3. So the opposite of dividing by 3 is multiplying by 1, or not opposite, but what dividing by 3 means is multiplying by 1/3. And then that whole flipping on the x-axis, so that reflection on the x-axis, that's where that negative comes from. And that -3 is that downward unit. Now notice again, all of those are vertical style movements. And again, those are all on the outside. Now you'll notice that when I talked about shifting to the right 2 units, that shifting to the right there, that was what we again called a horizontal movement. And anything that is a horizontal movement does mean I need to be inside the grouping symbols. Now remember, anything that's inside the grouping symbols, it's the opposite of what you want to think. So normally, because I'm shifting to the right, I would say plus, because that kind of logically is what we think about. Again, it's opposite of it. So instead of minus, I put a instead of plus, I put a minus. Okay, so hopefully you had a little bit of practice with that. I really recommend pulling out the graphing calculator or visually looking at a graph, and always start with your base function and then look at one thing, like what was one number do, and only work on that one number. Okay, so let's talk about symmetry now. Now, there is a couple of different symmetries out there. We have our first one, which is symmetry on the y-axis. Now, what I mean by that, and again, I get where sometimes we get a little bit confused by what that actually represents. So what I mean by basically symmetry on the y-axis is, so here is our base grid lines here. So here's x and here's my y. What I mean by that is you have some type of graph, and it happens to be perfectly symmetrical about the y-axis. So you'll notice I drew this kind of V shape here. That's my absolute value graph. Okay, so that would be a beautiful function of just saying the absolute value of x. Okay, this one here is actually perfectly symmetrical about the y-axis, meaning that for every x value, so if I have x equals 1, that y value is exactly the same when I look at it on the other side, where it would be for -1. Okay, so they would have the exact same y value. If I look at x equals 2, it's going to have the exact same y value as x equals -2. Now, how to actually say that without actually looking at the graph or looking at every single x and y value is basically if I take any function and I plug in negative x and I get the original function back, then that basically means that we have y-axis symmetry. So another way of saying it, and I'm going to erase everything on this slide real quick here. Okay. Another way of just saying that exact thing there is basically to check for y-axis symmetry. Oh, geez. Hang on. Okay. So to check for my y-axis symmetry, what we can do is basically you are going to plug in negative x. Okay. So you're going to plug in negative x for all x's. And if you get the original equation back, then you have y-axis symmetry. Okay. That's literally all you have to do. And that is actually what this says up here is if I plug in negative x for all x's and I get the original function back, then I have y-axis symmetry. It's just we happen to use function notation, and that's kind of the way a lot of things are written in math, is we like it to use function notation instead of x's and y's. Okay. Now, the other thing that we kind of want to point out is that if you have y-axis symmetry, so if you have a symmetry with respect to y-axis, then that function is actually even. Okay. They get a special name. We just call them even functions. Okay. Now, I'm going to try this again, and let's do origin. So if we have symmetry with respect to the origin, okay, a little bit different here, the origin symmetry, okay, symmetry with respect to the origin. Now, these ones here are called odd functions. Now, again, that function notation I know looks a little strange, so let me kind of give you the easier way to kind of think of this, is you're going to replace x with negative x and y with negative y. Okay, so for my symmetry with the y-axis, all we're doing is basically we are replacing x with negative x. That's all we did. But for origin, every x value is being plugged in as negative x, and every y value is being plugged in with negative y. Now, again, if I come out with the exact same equation that I start with, so the original equation, then we basically say that this function has symmetry about the origin. Now, origin symmetry is a little bit harder to visually see. So with y-axis symmetry, it's very easy. Just look at the y-axis, and if you can fold the graph in half along that line, then you have y-axis symmetry. Origin symmetry, you're going to end up with a little bit more in the sense of it's going to be kind of a reflection on the x and y. So like you have x and y together there. These graphs are going to look a little bit more like, say, y equals x to the third. That is actually one that has beautiful origin symmetry. So basically every x, y value, x, y point that you have is actually mirror imaged with a negative x and a negative y point. Okay. Now, again, there's three symmetries. So let's talk about that last and final one. The last and final one is our x-axis. Okay, so our symmetry with x-axis. And for this one, kind of the easiest way to look at that is you're basically replacing y with negative y. So maybe that kind of helps you out a little bit there. I know that they kind of go into this large detail of it, but it's really just whatever axis you're looking for. So in our case here, x-axis, plug in the opposite letter for negative. Okay, so instead of x, I'm plugging in negative y. And again, if you get the original back, it happens to be that symmetry about the x-axis. These ones here are a little bit harder to actually graph. Okay, so in your graphing calculator, most of these will not be ones that you can actually physically graph in the calculator. They do take a little bit of work to even try to put them in the calculator. So let's determine algebraically whether this equation here is symmetric about the x-axis, y-axis, or origin. And we'll try to graph it in the calculator to also kind of confirm it graphically there. So our original equation is y equals 2x squared divided by the quantity of x squared plus 1. So we'll start with x-axis symmetry. And again, x-axis symmetry means I'm just going to replace y with negative y. So, okay, well, there's only one y value, and I'm just going to plug in negative y. Now, I noticed there that straight away, I have one side that is perfectly original to the original function that I started with, but the left side where I plugged in negative y, it just stayed negative y. So that actually tells me straight away there that there is actually no x-axis symmetry. Again, I have to get the original function back. Even if I do like a little bit tweaking and divide, I'm never going to divide by a negative. Like I'm not going to get the exact same thing back as the original right here. So my whole goal is this is the original. I need to try to get this back exactly as I see it. So let's do our y-axis symmetry. And again, opposite letters. So since I'm looking for y-axis symmetry, we're going to place x with negative x. Okay. So everywhere I see x, I'm plugging in a negative x. Now double be super positive here that when you plug in, always plug in a set of parentheses around that negative, because again, you're replacing every x with a negative x. And I'm going to simplify. Now, when I plugged in here, I have a negative x and I'm power of 2. That now becomes negative squared is positive. So that's why this stays 2x squared. Same thing down here, that stays just a beautiful x squared. And I notice that basically I have a y equals, and then I have 2x squared divided by the quantity of x squared plus 1, which, yes, is exactly like the original. So therefore, we have y-axis symmetry. Now, with origin symmetry, you've got to do both. You are going to place x with negative x and y with negative y. Now, when I plug in x with negative x and y with negative y, I'm going to kind of do my simplification with the x's, but notice with the y, I can't really do much else than just leave it as that negative y. So I end up with this kind of like negative y equals 2x squared over x squared plus 1. And again, that left-hand side with that negative y is not the same as the original, but the right-hand side is the same as the original. So again, there is no origin symmetry here. Okay, and this is what this looks graphically. And again, remind yourself when I talked about those points, you can kind of see that it looks like it's been mirror imaged right along this line right here. Again, think of it straight, but I wanted to make it very, very visual there. As if you look along that line there, it looks like the graph has just been, I can kind of fold it in half and that these look exactly the same on either side. And because it looks exactly the same on either side there, we basically can say, well, what axis is this? This is the y-axis, and that's what it's symmetric about. Okay, let's try this again. So let's determine algebraically whether this graph has x-axis, y-axis, and origin. And again, we're going to try to confirm graphically there. So we'll start with our x-axis symmetry, and that means basically it's going to have replace y with negative y. Okay, so I replace y with negative y. Now, again, the first thing I always want to kind of look at is I've got at least one side that matched the original. So we can see that that's the original here. And so we have one side that does, but the other side does not match the original. Okay, so this side right here did not match the original. So it doesn't actually match the entire original, which means I can say the word no. Okay, let's go with the other version. Let's go with our y's. Okay. So y-axis symmetry means I'm going to replace x with negative x. Okay, so replace x with negative x. Now, again, I notice on this one here, I have the left side does match the original, but I'm noticing on that right side, it is not matching the original. Okay. Again, really paying close attention to the fact that this has got a negative and that's got a plus. Now, where did they come from? Well, guys, a negative times a negative makes that plus, and a negative cube just stays negative. So that's where that negative x cubed came from. Again, it's not exactly like the original. So my answer would be no. Now, just because it has x-axis and y-axis does not necessarily mean it won't meet the requirements of origin symmetry. So you always want to actually check for x-axis, y-axis, and origin. You always try for all three. So with the origin symmetry, I'm replacing x with negative x and y with negative y, both at the exact same time. Now, this one's a little tricky because once I replace it in and simplify out, I notice here, and again, this is a part where I'm at, where I've simplified it out, neither side matches the original. Now, because neither side matches the original, what I want to do is I actually want to make sure at least one side matches the original. If at least one side matches the original, then I can confirm and basically say there's just no way to make it work. But if I notice here, if I take this negative that's in front of the y and I just divide both sides by -1, okay? Notice what happens is that negative divided by negative is positive, and now we can see very clearly that this one side, and let me go back to yellow, yellow means match. Yellow, the y equals, matches that left-hand side, which also had a y equals. But notice on my right-hand side now, that x cubed minus 3x, again, that actually matched the original function that I started with. Now, again, I had to do a little bit of simplifying there to get it. But again, as I simplified it out, I at least made one side match and the other side just happened to follow along and match as well. So this is what we say origin symmetry. Okay. And because it's got that origin symmetry, again, what I'm kind of noticing is that if I have this x value here where x is 1 and y is -2, that point is going to end up being x equals -1, but the y value is +2. So literally, basically, x and y pretty much switch places in general across that origin. Every x became -x and every y became a -y, and it's a perfect mirror image across that with those x's and y's being flipped by signs. So if I were to just look even at a different point, again, here we have basically, let's see, it looks like our x values may be like a negative, say that's like a 1.75. Over here, it's a positive 1.75, but those y values are exactly the same on both of them. Okay, and so we can see that this one has a beautiful origin symmetry. Okay, let's try this again. Again, every single time I try this, I always want to test all three. So let's look at x squared plus y squared equals 16. Now this one's a little bit harder because I'm not going to be able to put this in the graphing calculator as nicely. You'll notice all the other ones said y equals, and this one has a y squared. So this actually is really hard for me to plug into the graphing calculator because again, we only have a y equals button. And so what I want to do is, again, try this algebraically out. And we'll start with our first part right there. And let's just replace y with -y, testing our x-axis symmetry. And again, as I plug in y with -y, again, start with those set of parentheses around it when you plug it in. And one thing I begin to notice is that when I plugged in my -y and simplified it out, I have the left side that matches the original and the right side that matches that original function. Again, here's that original. And since both the left and right side matches, we can say, yes, it does actually have x-axis symmetry. Now, again, just because it has one type of symmetry does not mean that it can't have another. So let's go ahead and try our y-axis symmetry. So we're going to replace x with -x. And again, as I do this one here and simplify it out, I happen to notice that, again, I get my left side matches and my right side matches the original. So again, yes, this one actually did have x-axis and y-axis symmetry. Now, again, double check every single one of these symmetries. You always want to check each one individually. So check x-axis and y-axis and the origin. So origin symmetry means I'm going to replace x with -x and y with -y. And again, as I look at that there, I end up with the original on the left side and the original on the right side happens to be exactly the same. So yes, it does have origin symmetry. Now, like I said, this is really kind of hard to graph in the graphing calculator, but this is what it would look like. And as you can see there, it's actually a beautiful, perfect circle. So we can see pretty nicely there that yes, it does have that y-axis symmetry. Yes, it does have the x-axis symmetry, and it does have the origin symmetry, meaning that if I were to take one of these points and if I switch basically the x and y and put negatives on it, I'm going to find that exact same point on that other side there. Okay, so they're basically perfectly about the origin, helping me out there with, for every point that I have x, y, I should have negative x and negative y, exactly the same point. Okay, so now that we figured out our symmetry, let's determine again if it's even, odd, or neither. Now, what I highly suggest is you kind of already started this process with the x-axis, y-axis, and origin. And that's actually going to help us figure out if something is even, odd, or neither. And yeah, you can also graph these and determine it that way by using the visual representation, but sometimes doing the algebraic way is really helpful as well. So in our first case here, we have y equals x to the third minus 2x. And again, I'm going to do x-axis, y-axis, and origin, okay? Again, for my x-axis, I'm going to replace basically my y with negative y and my x with negative x, and I actually mislabeled these, I'm sorry. So this one right here is testing for my y-axis symmetry, and this one here is testing for my x-axis symmetry, okay? So again, opposite letter is what's going in with the negative. So this is why this one's y-axis symmetry is because I plugged in my negative x, and this one's x-axis symmetry because I plugged in my negative y. Okay. Again, all I need is at least one side to match the original. So again, here's my original function. And I notice over here, this side matches, but this side does not. And on this one here, we have, again, this side here matched the original. If I divide by -1, I have this side that matches the original, but the other side doesn't. And then my origin, again, neither side left or right matches, so I had to divide by -1. And when I did that, both sides ended up matching, which means that I have origin symmetry, okay? Again, this is where, what I'm saying, like, it doesn't match. It has to match on both sides. Now, in our case here, both sides didn't match here. And since both sides didn't match, I always want to simplify out if I can. So once you plug in, if you have one side that matches, but be sure to simplify. That's the biggest problem that I find with a lot of students is they don't simplify here. So when I look at this one here, I say I'm not done because it's not fully simplified. Once it's simplified, then I can really make that determination. Now here, you plug in -y, that's as simplified as that goes. So you can kind of see automatically whether or not it passed or not. And over here, again, left and right side, I've got them in there. And again, the left side didn't match, but in the right side, if I were to simplify it down first, I end up with, and let me go ahead and switch to a pen. I end up here with basically a -x cubed plus 2x, which is again not what the original one is, but a left and right doesn't match. So therefore, that's why I divided by -1, and it happened to be just origin symmetry. And because this is origin symmetry, anything that has origin symmetry is what we call an odd function. Okay, so let me pull that up in the graphing calculator for you to actually visually see it. Okay, so I've gone into my calculator and I said y equals, and I have x cubed minus 2x here. And again, as I have that there, I'm going to hit graph. And I notice when I look at that beautiful graph, again, this is kind of that origin symmetry we talked about, where basically if you have a point, say here, where the x is +1, when I look at -1, the y value should look like it's been switched. So in my case here, my y was negative, but now it's positive. They're kind of opposite signs. They're perfectly symmetrical about that. If I have this point x, y, then if I say I should have -x, -y be the exact same point in that mirror image of it. So this is where that's origin symmetry. But we can see very nicely that it did not work about the y-axis or even the x-axis itself, okay? If I'm visually, when I look at this, this is what we call an odd function. One of the good things about that is you can kind of clearly see it. Now, an even function would look something like this. So this would be an even function, and even functions basically have y-axis symmetry. They're perfectly symmetric about the y-axis. Now, if I were to take this graph and shift it, and let's just shift it, how about, say, 3 units to the, let's go to the left. Oh, sorry, we got to start fully fresh there. So since I'm going to 3 units to the left, that should be parentheses x plus 3 quantity squared there. And when I look at that, again, the graph has been shifted to the left, but again, it's not symmetric on the y-axis anymore. Okay, so if I look at that y-axis, I can't fold that graph perfectly in half on this line right here. I can't even do it on this line right here. And again, there's no origin symmetry that this point doesn't show up over here. Okay, so that's why when we look at them, it's sometimes helpful to look at them graphically. But there are some of them that are not possible to actually visually see it. But these ones here, if you look again, if you can fold it, even and odd are definitely very easy to see in the calculator. So if it's even or odd, you should be able to visually see it in the calculator. And these are all the ones that have origin symmetry and they have y-axis symmetry. But there are a couple of cases with origin symmetry that you won't be able to put in your graphing calculator. And that was like one of the ones that was the perfect circle. There's just no way to put the perfect circle in there. That is easy to do visually. So you can't just, it takes a little bit of tweaking. So we don't actually put those in there, but that's why we do them graphically. And then I would do those more algebraically with that, replace y with negative y, replace x with negative x, and then do it both at the same time there. Okay. This is 4.1, which is transformations. I recommend that you definitely take a bit of time, learn your different transformations that you have. And then once you have the transformations down, this will actually come and help us later. And it also helps us with figuring out the domain and range of functions by noticing your base graphs. Now, I kind of want to just, as I leave you off here, it does help if you kind of go over some of your base functions. So this will be one of my base functions here, which is y equals x squared. You'll notice I also talked about the absolute value. Okay. And in my absolute value there, it would be like this one here. That is also a really good base function to look at. Okay. So that's a beautiful base function and we can kind of see there, and it's perfectly symmetric on the y-axis there. So therefore it is an even function. Another base function or a parent function that's really good to kind of make note of is that nice lovely x to the third. Again, I can clearly see that shape of the graph, and this one has a beautiful origin symmetry there. Okay. Another base function that I really kind of look at a lot in the homework is a square root function. And again, you can take a good look at that square root function there. Again, this one does not have any x-axis, y-axis, or even origin symmetry. So this one would be neither even or odd. But again, this base function here is a good one to see a lot of those transformations on. Now, be aware there are other functions that we do our base transformations on itself. I can even get a little bit more complicated with it and use like a fraction function. So like 1 over x is another good one that I can look at. I can take this graph and move it up, down, left or right, or even stretch it or shrink it. But again, always kind of take a peek at those base functions and learn a little bit about them. And they'll kind of help you when we start getting a little bit more complicated with them, we can see the transformations that happen on them a bit better.